How much time does it take for light to travel from the moon to Earth? Distance of 384,000 kilometers. All right, so this will be the moon. This will be Earth. That's supposed to be a little squiggly thing. That's D for distance. We're going to use old reliable. Velocity equals distance divided by time. Therefore, if we're looking for time, so I'm going to for time. Time equals distance divided by velocity. The distance in this case is going to be, I'm going to write this as 3.84 times 10 to the 8th meters. So we have 3 zeros from kilo, 3 zeros from the 3 zeros, then I move the decimal place over 2. That gave me 8 decimal places. You're like, wow, that's an awfully specific number. Yep, and that's because I'm going to use 3 times 10 to the 8th meters per second as the speed of light. Some people use 2.99 times 10 to the 8th meters per second for light. The actual number is going to be closer, like 2.997 times 10 to the 8th. The reason some people, I know this is tangential, will use 2.99 instead of 3 is because nothing goes faster than the speed of light. So when they use 2.99, the idea is they want to err on the side of slower than faster. It's actually more accurate, closer to the actual number, to use 3. Some people just don't like to go over the speed of light, which is understandable. It's kind of a philosophical thing. Not a big deal, more nuanced than you probably care for. So 10 to the 8s cancel, we go to our calculator, and we get on 3.84 divided by 3, and we get 1.28. Now I'm going to check, see if they ask for the distance, or if they're asking for the distance there and back. How much did I take to travel from the moon to the Earth? Okay, so yeah, maybe 1.28 seconds. So sometimes those kind of questions will ask for basically like if you shoot a laser beam at the moon, how long does it take to get there and back? So basically you just take this question and you double it. So 1.28 seconds. And that's the idea that the speed of light in a vacuum is constant, about 2.99 times 10 to the 8th or 3 times 10 to the 8th meters per second. And yep. So light from a star, Sirius, takes 8.61 years to reach the Earth. What is the distance to Sirius in kilometers? All right, same question. Velocity equals distance divided by time. We want to know distance now. So this is going to be distance equals velocity times time. The velocity is 3 times 10 to the 8th meters per second. Times time, which in this case is going to be 8.61 years. So I'm going to do 8.61. I'm going to do years. So this is basically asking us the distance of, what is the distance of 8.61 light years, which is basically how far light will travel in 1 year. So what we're going to do then is we're going to convert this. So 1 year, this is just going to be dimensional analysis. Dimensional analysis looking at what the units are. We're going to convert units. 1 year, 365, that's supposed to be a 5 days. We're going to have 1 day is 24 hours. 1 hour is 60 minutes. And 1 minute is 60 seconds. And so now we're going to look at all the units, make sure everything cancels appropriately. So we have minutes, hours, days, years, and seconds, and we are left with only meters, which is what we want. So what I'm going to do is I'm going to multiply this out. So we have, actually I'm just going to do the second portion over here. You'll see what I mean. 365 times 24, oh, clear. 365 times 24 times 60 times 60. And that gives us, so then we're left with 3 times 10 to the 8th times 8.61 times, I think it was 3.15 times 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. And so one of the things you'll see from time to time as almost a joke, almost a mnemonic, is that right here is 3.15 is almost pi. So you're like, well, there's pi times 10 to the 7th seconds per year. So if for some reason you're strapped for time and you don't want to go through this whole second portion here, converting number of seconds in a year, you can kind of use the mnemonic, there are pi times 10 to the 7th seconds per year. Just coincidental, part of life, not a big deal. All right, so now though, we're going to 3 times 8.61 times 3.15. So it's 8.61 times 10. I'm going to do 10 to the 15th. And what I just did there was I added the 8 and the 7, because when you multiply exponents, well, when you have bases that are the same and you're multiplying two bases with exponents, you just add the exponents. So that gives us 8.14 times 10 to the 16th meters. And then we'll check to see if that is the units that they wanted. Nope, they wanted kilometers. So I'm just going to take off 3 from the 16, and we get 8.14 times 10 to the 13th meters. And that's how far 8.61 light years are. That's L for length. So not too big deal. These couple questions, it's just velocity equals distance divided by time. And the concept we're going for here is that the speed of light is constant. And what that really goes into is that the speed of light is constant in a vacuum. So you might have learned this already, might not. There's something called index refraction, written as n, which is basically the fraction of the speed of light, or how much slower light goes in a medium that is not vacuum. So at vacuum, normal speed of light 2.99 or 3 times 10 to the 8th meters per second, and everything else goes a little bit slower. And here they say consider electromagnetic waves propagating in air. Well, the index refraction of air is something small. By small I mean about almost 1, so it's like something like that. And so when you divide 3 times 10 to the 8th over how much slower it's going, it's basically the same. So whenever you see propagating in air, that's basically the same as propagating in a vacuum or space. When you see propagating in something like water, that's actually about like 1.33. That's actually significantly slower, and you have to actually take into account how much slower the speed of light's actually going in something like water. But for air, you're like, it's basically the same speed as vacuum. Not exactly, and there are some significant effects that come from that. But for most of these problems, we're fine. We'll call it, it's close enough. All right, determine the frequency of a wave with a wavelength of this. All right, so this is very similar concept, except now the formula we're going to use, I start with velocity equals distance divided by time, and I use dimensional analysis to basically find this formula. So V for an electromagnetic wave is going to be C. This V is the speed, C is the speed of light. Instead of distance, we're going to use the wavelength. So wavelength has a unit of meters, so does distance, and 1 over time, well, that's 1 over seconds, which is the same as hertz, which is a unit for frequency. So I use the velocity equals distance divided by time. I have the memory of a goldfish, so I try to reuse as many formulas as I can, as many mnemonics as I can to memorize things. And so this is how I memorize this formula: C equals lambda f, where speed of light equals the wavelength times the frequency. And from this, we're just going to solve everything. So determine the frequency of a wave with that. So we're going to say wavelength equals C divided by f, formula above, just rearrange 3 times 10 to the 8th because it's convenient, divided by frequency. Oh, nope. We want to find the frequency. Fail, tragic. All right. Round 2. Frequency equals C over lambda, 3 times 10 to the 8th over, and we're going to have to use meters here, 5.2 times 10 to the 3rd. And this is going to be equal to And when I put this in the calculator, I'm going to do 3 over 5.2 times 10 to the 5th, because the 3 on the bottom will cancel with 3 on the top, which gives us 8 minus 3, which is 5. This right gets something to the 4th. 3 divided by on, clear. 3 divided by 5.2 times 10 to the 5th. We get 5.8 times 10 to the 1, 2, 3, 4. 5.8 times 10 to the 4th equals 5.8 times 10 to the 4th, and that's going to be hertz. 5.8 times 10 to the 4th. Okay, determine the frequency of a wave of that. So now, same question. 3 times 10 to the 8th over... Nope, they gave us a frequency. Fail. We want to... oh, no, that's correct. They gave us a wavelength. Because this is a big wavelength, this is a small wavelength. 3 times 10 to the 8th over 5.8 times 10, this is going to be negative 6. So now we're going to have 3 over 5.8 times 10. 8 minus negative 6 is actually going to be 8 plus 6, which is 14. And so this is going to give us something like 10 to the 13th. So 3 divided by, clear, 3 divided by 5.8 times 10 to the 14th. And we get something like, 5.2 times 10 to the 13th equals 5.2 times 10 to the 13th, and that's going to be hertz. 5.2 times 10 to the 13th hertz. Okay, determine the frequency of a wavelength of that. Same concept. Frequency equals 3 times 10 to the 8 over 5.8 times 10 to the negative 9th. Negative 9th is nano. And so this is going to give us pretty much the same thing. It's going to be 3 over 5.8 times 10 to the 8 plus 9 is 17. So it's going to be the exact same answer as before, except it's going to be 3 higher. So it's going to be 5.2 times 10 to the 16th. I know, questioning myself, self-doubt. I should be more confident. 3 divided by 5.8 times 10 to the 17. That gives us 5.2 times 10 to the 16. Yes, so I was correct. Good for me. Go team. Right here, 5.2 times 10 to the 16th hertz. Okay. So now we got that. What is the wavelength in meters of gamma rays, which is just a specific band, a frequency band of electromagnetic radiation. And we want to find the wavelength. So we're going to go back to our formula. I know you think I'd have it memorized. I don't. So wavelength equals C over frequency, which is 3 times 10 to the 8th over 6.46. They're going to be very small wavelengths, times 10 to the 21, which is 3 over 6.46. 8 minus 21, I think that's 13. So it'd be times 10 to the negative 13th. The negative 13th means that it's the 10 to the 13th is on the bottom in the denominator. So when I put that into my calculator, clear, 3 divided by 6.46 times 10 to the negative 13th. 3.46 times 10 to the negative. Yep. That gives us 4.6 times 10 to the negative 14th. Yes. 4.6 times 10 to the negative 14th, and that is meters, and that is the wavelength. So one thing that you'll notice is that basically the energy associated, and we'll get to that in later problems, the energy associated with a electromagnetic wave, I'll write it as L gamma for a photon, it has to do with how compressed the wave is. So if you have a photon like this, I know, very compressed, it's going to have more energy than a photon with a larger wavelength. Smaller wavelength, more energy. I like to think of it as a spring. When you have a spring and you compress it, the little up and downs of the spring get closer together, smaller wavelength. Not quite an exact analogy, but for mnemonic, it's adequate. All right, what is the wavelength in nanometers of this exact same wavelength, gamma ray? So what we're going to do is we're just going to convert it. 4.6 times 10 to the negative 14th meters. 1 meter is 10 to the 9th nanometers. The meters cancel, and we get 4.6 times 10. Negative 14 plus 9 is negative 5. This is a very energetic photon. 4.6, actually I wonder how energetic it is. I should calculate that out. It's okay, some other time. 4.6 times 10 to the negative 5th nanometers. Very, yes. Lots of energy, very small. So, and that's how we do these. Basically the idea here is we, speed of light is constant in a vacuum. It obeys the law, velocity equals distance divided by time. And that is related to the speed of light is the wavelength times frequency of the electromagnetic wave that you're talking about. Hope that helped. See you next time.